crucial.
Yeah, I heard you guys scream.
Dude, that has to start with a P. Pack.
No. Ew.
Oh, you got
I got pizza and jalapeno. Help yourself.
Oh.
What? Are we
what?
chopped liver? Literally like chopped?
Yeah. Hey guys, look at what I'm doing.
Good job.
Good job.
Epic.
Good job.
Derek Mac
Yeah,
and
like,
Mac.
good job, I think.
Oh, this is like, it's literally called, listen, it's called Quiz number 5, pre-review with Nutty, Mars, Kath, and HJ.
Spoilers, the review guide for this quiz is basically just going to be this packet again, because it's all just proofs, right? Like, I can change the triangle shape, but it's going to be the same dumb crap.
I get one of those.
Yeah.
Kind of slow. Okay, Hannah should not be allowed to answer all the questions because Hannah's smart.
Yeah.
And Kath.
I don't understand this, so I'm just gonna like.
I think you guys need to all chill and let Hannah do her own
You guys are
thing.
being really loud. I'm sorry. It's okay.
It's true.
Yeah, Mr. Mac.
All right, I'm closing this so the track people don't.
Sorry, Mars, I love you. There's cough drops. Are they empty?
No.
I'm confused on the last one, so we're
Is there an empty wrap?
not do it.
The last one's really hard, but yeah, take a break for now. Yeah. A break doing
Mars,
this.
I'm proud of you.
See if this
I love
Are you
you.
the smartest of us
Oh.
all?
You guys all have plans. Stop. Dude, I bought you $350 worth of gummy worms today, so 350 cents.
Actually, we should multiply that by times 0.00001.
Wait, point zero. Yep.
Math.
Math.
Dude, I'm gonna fail algebra 2 next year. Oh my.
No, you're not. No, you're
I
not.
put on my sure.
If you can survive my class, you're gonna survive algebra 2. You really will. Also, I'll be right here.
I didn't
And apparently the teacher is.
I cried every night.
I think it's Royer.
Oh, guess what, Mr. Mack? You'll be seeing me next year, so.
Yeah, that's okay. I can help you.
Fourth
Trust
hour
me.
Next year.
Algebra is a joke compared to geometry.
I'll
Can I switch to 4th hour or go sit in my old
No,
spot? Because I
no,
literally
no.
love that spot.
I know.
I miss 4th hour.
I was hand hour. Hand wasn't.
Can we do this instead of talking?
Yeah.
Because you guys need to get out of here, right? Eventually.
Yeah.
And then I need to do work to prepare for tomorrow.
We can help you.
Someone wants to come in.
Yeah.
Let him start.
Okay.
Tomorrow.
Tomorrow's review, so I have to make all the review guides and basically make all the quizzes. I will, but then I have to do it for algebra as well because they're taking a quiz. Same thing with basic geometry.
Can I retake quiz 1?
And I need to do all the grades that you guys keep whining for me to put in.
Yep.
Right? And not whining in a bad way. I mean, like, you should be. But, like, I chose not to work more than 14 hours a day.
Can
Yeah.
I retake quiz
We
1 during study hall?
appreciate all of
Yes.
the work you put
Yeah.
in.
Yeah, I don't think.
And
I
next
know.
time we come in,
I know.
we're going to order you a pizza and get it.
Appreciated but not necessary.
You could just have my credit card.
Appreciated but not necessary.
Just have my
My house is right there. I'll have it delivered there, and
Let
then I'll
him
run over
start.
and pick it up.
Oh my gosh.
Yep. You think first hour's bad? Oh, my God.
Fourth
Okay.
hour, fourth hour.
Here we go. So,
I was annoyed.
let's prove this lemma. That this is true. So, let me first, before I get into this, work with this a little bit so I can show you what our goal is, okay? So I'm going to mess around with this thing right here, okay? I'm going to do this. I'm going to move b minus d over by multiplication, right? I just multiplied that whole thing over. Are we cool with that? Rabbiting parentheses. That's a c.
Can I watch?
Yeah, please. We're going to go over it tomorrow, right?
Oh yeah. I'll just...
So, yeah. So, look, I multiplied by b over d to move it over, right? We good with that?
Yeah.
Okay, is everybody good with this algebraically, what I just did? Do not just say yes, be honest.
Hey,
Actually look
I'm
at this.
curious about-
I took this, and I just moved
yeah,
over
yeah.
b minus d,
Yeah.
Oh, because you tell me just
right? I moved it all at once over, right? And we will distribute. Yeah, we will.
That's what that is, though.
By moving it over, no, I just multiplied, right? If that was if that was a minus c over 2, you'd move the 2 over by multiplication, right?
Wait, I don't get it.
I treated this just like it was a number, that whole thing. And so I moved it over by multiplication,
Oh.
right? Now, again, you have to wrap it in parentheses because you would distribute,
Oh,
right?
It's multiplication because it was a good number.
Yep, exactly, right.
Can I get a drink?
So, this is just like fourth hour.
I'm getting a drink.
Okay, go for it. Good Lord. All right, so my goal is going to be to find out what A is and what C is, and then I'm subtracting and I'm going to get this and I win, okay? That's the idea. I'm going to find out what A and C are. So notice I have this, right? I start with this. Let me write that nice and big, which will take up some time for Marissa to get back.
Wow. Oh, sorry.
Right? I'm given that. So I'm going to take A and find out what it is. I want it in terms of E and F, so I'm going to leave out the middle guy, okay? So how do I get A on its own in this case? How do I get A on its own?
Multiply by B.
Yep. So what I get is A equals BE over F.
Okay. Okay.
There's no hope for these scumbags.
Who said I owe her money? Yeah, she ate all my gummy worms.
What is it?
It was my one.
It tastes like coffee.
So I wanted to get A on its own and C on its own. That way I can say, I can do A minus C and I'll get this and I'll win, okay? So A, I'm gonna get it in terms of E and F. So I multiplied by the B, right? And I got this. We cool with that?
Uh-huh.
All right.
I am. I was actually paying attention.
C, I want to get on its own. So I'm going to work with this. Again, I'm choosing to get it with E and F. Trust me, you just need to do that. I don't want to explain it right now. What?
How come B is on top?
I was here, and I multiplied by B.
But like, how does it get on top?
So multiplication happens in the top of fractions, and divisions happens in the bottom, right? Okay? Yep, good question. So C, when I multiply D over, it's going to end up on top, right? DE over F. We cool? Right? So what is A minus C? Because I'm allowed to just subtract things whenever I want, right? That's totally fine, right? You take two numbers and subtract them. Well, what is A minus C? Well, now I know what A is. What is A, Marissa? What's A? What do we find A to equal?
B E over F.
Oh, thank you. I'm not on it. I'm not even looking at it. B over F.
Good. And what's C?
D over F.
Good. So when I subtract A minus C, I'm really subtracting BE over F minus DE over F, right? And now, notice they have a common denominator, right? If it was all like 1/3 minus 2/3, right, we could put them together. So I can rewrite that as BE minus DE over all over F, right? Common denominator. We cool with that? And I'm going to pull out the E, since both of these have an E. Now, if that confuses you, check. Go backwards. If I distributed the E, I would get this, right? So I didn't break math. I just made it look different. This is just a fraction, right? And we're multiplying by this. What's your question?
Since there's, you can cancel out, or you can't cancel out F, but you can cancel out B, or the, oh wait, no, you can't.
No, you can't. No, nothing.
Wait, why was subtracting?
Because it's up there.
So my goal is to get A minus C and get all this, because once I get there, I can work backwards and get to here and I win, okay? So now I'm here, right? This is the same as that. It's just E over F times B minus D, right? Same thing. Totally the same thing, right? And now I'm going to move over B minus D the way I did before, but in reverse. I'm going to divide it. So I get A minus C divided by B minus D equals E over F, and I won.
Can you move it up?
Yes. Sorry.
Wait, you won.
Okay, that makes sense.
That was the proof. That's what I needed to prove, right? If this, then that,
Oh.
right? Cool. Now, again, how did I know I wanted to get A and C on their own? Because I messed with this a little bit, and I knew if I got A and C, this should naturally happen, right? If this is true, if this statement is true, then this should naturally occur somehow, right? So I need to figure out what A and C were. I did. Then I subtracted them to see what happens, and I get this. Now I need to make that look like this. So I did this. I got there, and then I went backwards to here, which is where I really needed to be. We cool? Right? So I just did this to show you why I did what I did. You don't have to do that.
So the part in the brown is just like a more simplified version of the.
Of this, yeah, I just moved it over so we can see what our goal might be, right? One goal would be to find out what A and C are, so when I subtract them, I should get that, right? Cool.
What did you say?
Boner.
Yeah?
If we were to like do it in a different order and still end up with the same thing, wouldn't matter.
As long as you didn't break math on your way to it, yeah, that's fine.
Okay.
Right? All your steps have to be valid, but yeah. So that's the proof of the first lemma, okay? We're going to use this fact that when this is true, we're going to use that later in a proof, right? Okay? That's what it means to be a lemma. All right, turn the page. Next lemma, lemma number 2. All right. The area of a triangle is proportional to its base and height, right? Area of a triangle is this. Cool. So the logic is this, that if these triangles have the same height, and they do, right? Triangle, this one, the red triangle, and the blue triangle have the same height, right? They do. Do we see that, Marissa? These two triangles have the same height, right? So if they have the same height, when you write their areas, so area of the blue triangle, well, that's its base. What's the base of the blue triangle? C. Times height, which is h for this problem, right? I'm going to do it in black even though I did it in red, sorry. All over 2, right? That's the area of that
Are you
triangle.
just like plugging in the variables for?
Pretty much, yeah. I'm showing you this interesting fact, okay? So we know that that's the area of that triangle, right? What's the area of the red triangle going to be then? What's its base? Okay. Yep, because they have the same height. If they had different heights, I'd have to call it something else, right? We cool with that? So what happens? Oh, another way to write this, just so we're clear, is half CH, right? And half DH, right? Right? We all good with that? Yeah.
I'm confused. Why is it C?
What's the base of this triangle? Little c.
Oh my
What's the
gosh.
base of this triangle? It's okay, it's okay.
I was looking at a different
It's
triangle.
fine. You were looking at the big guy, yeah. I know, that's fine. All right, so check it out. What happens when I talk about the relationship between these two triangles area, right? We show a relationship by division, right? Because if you divide two numbers, it tells you their relationship, right? What's 6 divided by 3? 2, because the relationship is double. Does that make sense, right? Division shows relationship. So I'm showing the relationship between the areas. How do they relate? Well, they relate the same way that their bases do. Let me show you. So the area of the first triangle, right, we said was half CH, right? Right, of the blue triangle? We cool with that? Right? The area of the red triangle is half DH. Right? That's okay. Letters are hard. So, what's a half divided by a half? What's a half divided by half?
1/4.
Try again. Any number divided by itself is 1, right?
One.
So that's 1. What is h divided by h? I don't know what h is, right? It could be anything. But it's going to be the same both times. So it's any number divided by itself is 1. See, when the heights are the same, you can do that. Right? If the heights were different, they'd be different numbers, so they wouldn't be 1, right? But the heights are the same. Katie, you with me? Okay. So what's 1 times c times 1?
C. 1.
And d times, all those went away, right? That's 1 and 1, so it's just d. So this tells you that the area of the blue triangle relates to the area of the red triangle the same way their bases relate. So that means this. If the area of the blue triangle was 24 and the area of the red triangle was 12, how do those numbers relate?
2.
Double, right? 24 divided by 12 is 2, right? Right? Now, if the base here was 6, right? We know since they have the same height, 24 divided by 12, the areas, the way they relate, right? Double, should be the same way their bases relate, right? So if this relationship's double, right? The bases should have the same relationship. That's what equal means, right? The same. So the areas relate the same way the bases do. So if the areas relate by double, what will the bases relate by? Double. So if this is 6, what will this be? 3. Right? That's true when the heights are the same. That's true, right? We cool with that? That's our second lemma. So when the height's the same, then the areas and bases relate, okay? First lemma was that big equal statement, right? You can rearrange it to get the minuses, right? Cool, yes.
But doesn't, like, if you have two things, don't they always relate somehow?
Yes, but the fact is that not that just they relate, right? That's uninteresting, right? I can take any numbers and put them in a fraction, right? So now 7 and 3 relate. How? By 7/3, right? What's interesting is that they relate the same way as the bases. So if this is double, then this is double. If this is triple, then this is triple. That's what's interesting. Great question. Hannah.
What is the definition of a lemma?
Lemma is basically a preemptive proof before you get into the big proof. Like, before I show you this really complex proof, I need you to understand these things, right? Before I teach you calculus, I need you to understand algebra, right? Those are lemmas, right?
So pre-proof.
Yeah, basically. It's like, yes. So,
We're in simulation.
wow, that's exactly what I said. All right.
Wait,
Yes.
I'm confused on how. I'm confused on how you got 3 and 6 for the bases.
What?
I'm confused on how you got 3 and 6 for your bases.
I made that up. I was using an example.
Oh.
If this was 24 and 12 and this was 6, then we'd know that has to be 3, right? If that was 24 and 8, the relationship would be times 3, right? If it was 24 and 8. So this would be 6 and 2,
That's a lot of math.
right?
I can't do that.
The relationship would be the same. It's not always double, right? But it's whatever it is here, it'll be here, okay? Put the phones away. Like, I swear to God, like, why are you here using my time but not, like, using it fully, right?
I've not been on my phone.
That's great. No one cares. All right, so
I care.
what is a Sevian? We need to know a definition as well before we go in. So 2 lemmas and a definition. What is a Sevian? It's any segment that connects a vertex to the opposite side. So, examples of Sevians. That's a Sevian. Vertex to opposite side.
Isn't that an orthogonal?
Right? Not necessarily. It looks like it. Right? That's an example of a Sevian. What kind of Sevian is that?
Median.
Yep. How do you know it's a median?
Because they're equal. That's why.
Yep. So medians are Sevians, right? They're a specific kind of Sevian. Cool? Is an orthogonal a Sevian?
Yeah.
Why?
Because it from vertex to.
Vertex to an opposite side, right?
Excuse me.
So an orthogonal is.
Hi, Mom.
Okay?
It's gonna be a hot second. Are you here?
They literally just started because they're butt heads.
Well, we decided to put garbage on the walls for like an hour, so it would make me better to just go home and then I will walk home.
Ooh.
I'll walk
I
with
need
you
a
guys.
ride.
Right now?
Mr. Mac.
We're doing it live. Watch it live.
Okay, I can just watch it later. I'm coming.
I'm sorry, Mr. Mac.
It's okay.
Sorry, my mom is-
I can literally teach you all of this stuff in an hour. Everything we've done. Everything we've done. From the ground up.
You only took like 2 minutes.
If you're
to do
here.
that one.
I know, but only if you're here. Like, really here. No, what I mean is, like, be here, not here.
Yeah.
Or, like, chatting, right?
Alright.
It's okay. I'm here, right? I'm here anyway. But I would eventually like to go home. So,
What kind of pizza do you
no. What kind of line segment is that?
An angle bisector.
Angle bisector because it bisects the angle.
Whoa.
Is an angle bisector a Sevian?
What's the...
No.
A Sevian is anything that goes from
No.
vertex to the opposite side.
No.
Not
Does it go from the vertex to the opposite side?
And that one.
Yeah.
That one it does.
But
Think
we
of
know that.
any triangle you make when you do an angle bisector, right? If it cuts the angle in half, right? In half, right? It will go from here to the opposite side, right? It's going to head away. It's going to hit that opposite side at some point, right?
Wait, so it's always, if it's an angle bisector, it's always a C.
It'll always be a Sevian, yep.
I thought angle bisector, I didn't know they had to be.
Now, you might think, wait, orthogonal sometimes, like for an obtuse triangle, let's do this. Oh, God, this isn't going to work out well. Okay, let's draw a better one. All right. God, I'm losing my mind. Okay. All right, so this is an obtuse triangle, right? An orthogonal is anywhere from the vertex down to 90, right? Anywhere in here isn't going to be a 90-degree angle. Do we see that? Right? So my orthogonal's here. It's where this side is extended.
So that's what you mean by like outside and inside?
Yes.
That one would be outside.
Mm-hmm. So the orthogonal's outside, but if we extend the line, it does touch the opposite side, right? So that is still a Sevian because it includes extending the side, right? So that's still a Sevian. Orthogonals are always Sevians, even when they go outside, okay? Now, perpendicular bisectors can sometimes go outside, but here's the thing. Perpendicular bisector means it bisects a side, right? And it goes up at 90 degrees. Is that a Sevian? No. Very rarely are perpendicular bisector Sevians. So Seva's theorem is going to work for all these guys, pretty much, Orthogonal has a special proof, but it'll work for these two. It's not going to work for perpendicular bisectors, and it's not really going to work for orthogonals because orthogonals are kind of complex, right? But we are going to use Cephas theorem to prove that these are concurrent, okay? So what is Cephas theorem? It says if you have cedians, like in this triangle, A, E, B, F, and C, D, right? These are all cedians, vertex opposite side, vertex opposite side, vertex opposite side, and those cedians are concurrent, right? Because I can draw a triangle, and I can draw a bunch of cedians, right? Are those concurrent? No. They're not all intersecting at one point, right? Are they cedians? Yes, vertex to opposite side, vertex to opposite side, vertex to opposite side, right? But they're not concurrent. But if they are concurrent, like this one, right, these ones, then the way it divides the triangle up, their ratios will all multiply together to equal 1. So the relationship between A and B times the relationship of C and D times the relationship of E and F will all equal 1. Yes.
So, concurrent means they all intersect at one point?
Right. So these lines right here, concurrent. These lines right here, not concurrent. Okay? So if we have a bunch of cedians and they're concurrent, the way they divide the triangle up, A over B times C over D times E over F, will be equal 1. That's Cephas theorem. Otherwise, they wouldn't be concurrent. Okay? So that's Cephas theorem. Let's prove it. So here's a triangle. And they tell you that you have a bunch of cedians that are concurrent. Okay? So we're going to prove that A over B times C over D times E over F is 1. Okay? So here's how we're going to do it. Remember our first lemmas, right? One was that weird, like, fraction thing with the minus signs, right? And the other was if the triangles have the same height, then their areas are proportional to their bases. Remember, proportional means that the relationships are the same. Okay? So check it out. This triangle, CDA, and this triangle, CBD, nice, have the same height, don't they? So their areas are proportional to their bases. I'll say it again. ACD, its area is proportional to A, and BCD is proportional to B. Okay? So I'm going to write that. The area of triangle ACD over BCD's area are proportional to the bases. What's the base of triangle ACD? Little a, right? You could call it AD, but we're going to use little letters, okay? BCD, what's its base? Little b. And we know that this is true because the heights are the same, right? I proved that earlier in a lemma, right? You don't have to say why this is. It's just from a lemma, right? So we know that. Now, what other triangles in this diagram have the same height and have A and B as their bases? GDB and GDA. Yep, these two guys, right? So I know that area of the triangle GDA, I'll go ADG. How about that? Keep it alphabetical when I can. And then BDG. Now, what's ADG's base? Little a. And what's BDG's base? Little b. So basically what I'm saying is this equals A over B, and this equals A over B, right? So I have something where I have something over something equals something over something equals something over something. I have A over B equals C over D equals E over F, right? That's our first lemma. I have three ratios equaling each other, right? So I should be able to say these two minus each other gets this. Do you remember that, right, from the first lemma, right? So when I have something like this, then I'm allowed to say this, right? We proved that in the first. Marissa, are you with me? If I have this, I can do this, right? We proved that earlier on. Well, I do have three ratios equaling each other. This ratio equals A over B, and A over B equals this, right? So I can take this guy, area of triangle ACD, and I can subtract this guy, area of triangle ADG, over the bottom guys, right? And it should equal A over B. All right? Now, here's the thing. what is the area of this triangle minus this triangle? So let me show you. This guy, the big guy, right? We see it, right? The big guy on the left. Triangle ACD, right? Minus this guy. ACG, this triangle, right? So in other words, this is the area of triangle ACG, this guy. Are you seeing it, Marissa? Are you seeing it? Okay. And what's this guy minus this guy?
How does that equal the base, though?
It doesn't equal the base. Their relationship is the same as the relationship between the base, right? If the areas are double, then the bases will be double, right? Does that make sense? Or triple or quadruple or a quarter, right? Whatever it is. We don't know what the relationship is, but it'll have to be the same. You cool with that? All right, now I'm going to do the same dumb thing for all the bases, all right? So if I flip the triangle, big triangle here goes with C. Big triangle there goes with D, right? Right? Little guys go with C and D, and they have the same height. So what's left over? This guy and this guy. So I'm going to cut to the chase. By the same dumb logic, these two go with C and D. All right? So I'm going to say, by the same dumb logic, I know that this guy right here goes with D, and this guy right here goes with C. Cool? All right. So I'm going to write area of triangle ABG over triangle ACG equals C over D.
Is this the thing that is even taught in class?
Yes. Okay, we good? All right, I'm going to zoom out. Same thing for E and F. This triangle and this triangle go with E and F, right? So BCG is going to go with ABG. Let's do that. This guy goes with E. This guy goes with F, right? Now here's the magic. I'm going to prove that when I multiply these guys together, I get 1. So A over B times C over D times E over F. What does that equal? Well, it equals this guy times this guy times this guy, right? A over B is this, right? C over D is that. E over F is that. You would write that. But here's the thing. When I multiply, I've got ACG in the top and in the bottom. What's ACG divided by ACG? 1. Right? That was A over B times C over D, right? What's ABG divided by ABG?
Could you write it?
Yeah.
Grace and Nutty?
Look at my watch face right now. I don't know why it's on. I don't remember putting it on there.
And we're all sitting by each other.
Wait, but Hannah's not in the middle. Hannah's always in the middle because she's a cheerleader.
We know.
All right.
My name is Hannah, and I am snapping Chet with his hood. And
Right, we are live again,
Is
apparently.
all-
Oh, God. No changes. No changes. Okay. Back to math. All right, so last thing, right? Notice that we have BCG on top and bottom, right? So what's BCG divided by BCG?
1.
1. So therefore this equals 1, and we're done.
That kind of makes
That makes sense.
Second time's always using the first, right? Also, you guys are actually trying to learn it instead of just like, I have to be here right now,
Yeah,
right?
it's kind of really distracting in school.
Mm-hmm. Yep.
Especially with Danny.
Third hour, yeah, it doesn't work well.
First hour.
But you know what? Let's be honest. You guys are enough of your own distractions anyway, right? You really are.
Can I get like a different seat? Because it like feels weird when I sit in the front row.
You don't like sitting in the front
I
row?
would sit right there.
Like it's like, yeah, can I sit like, can I sit
You
like
honestly think being further away from me would help?
Okay, but like,
Can we discuss this at another time when we're not live and
Oh, sorry.
when I'm not wasting your time?
Yeah,
Right?
sorry.
Okay. No, it's great. I'm wasting your time. You're not wasting mine.
Oh.
All right. So now we're going to prove the converse. So if we're told that these all multiply to equal 1, we're going to prove that they must all intersect at a point, right? So we have 3 random Cevians, right? And they divided our triangle up in a way that they all multiply to equal 1. We're going to prove that the Cevians that we drew must all intersect at one point, okay? It's the converse, the reverse. So here's what we're going to do. screw this triangle, okay? Let's look at this one. Two cVians intersect at a point. We agree, right? My third one that I'm going to draw that supposedly divides it up into A, B, C, D, E, F such that they all multiply to equal 1, right? I'm going to draw it here. And I'm going to prove that in order for this to multiply and equal 1 like it said it did, right, that must actually go through this point. Okay? Here's my logic. See if I can do this. I'm very, very tired right now. This is a proof by contradiction. Sort of. Okay. All right. All right. So we know that this is true. Right? That's what they gave us, right? Do I want to do this one right now?
You do not have to.
I think I want to do this one later.
That is A-okay.
I think I want to refresh myself on how to do this proof so I can streamline it. I can do it, but I'll have to fumble around a little bit until I get my groove, and I'd rather not have you guys sit through that and get confused by it. Let's flip. We'll do the converse later. All right. Let's skip to 9. Page 9. The actual review guide will be ordered differently, and I'd rather do this order for the review guide. It's okay. So, we're going to prove that medians of a triangle are concurrent, okay? So here's how we're going to do it. We're going to prove that when I draw the medians in, they're going to divide the triangle up into A, B, C, D, E, F, such that when I multiply all together, everything gets 1, right? And then by the converse of Siva's theorem, if they all multiply to 1, then they must be concurrent. Okay? So I'm going to draw some medians. Let's draw this median. Okay? It's a median, so says me. So the way I do that is I say let CD exist and let AD be congruent to BD. Cool? That creates a cVian. We good with that? Okay. I'm going to do the same thing here. Let AE exist.
Is this what we're doing today?
It's very similar. Let AE exist, and let's have BE be congruent to CE. Cool? Right, so that creates a median. Now, the last median, right, they intersect at some point, right? The last median that I draw doesn't necessarily go through there. I'm going to prove that it has to. So I'm going to draw this like this, not necessarily going through that point, right? We're going to prove that it actually does, but for now, let's just do BF. So let BF exist such that AF and CF are the same. All right? So, I'm not going to use little a, little b, little c, little d, little e, little f, okay? I'm just going to use the letters I have here. If you want to say let AD equal little a and let BD equal little b, you can. I'm not going to do that, okay? Here's what I'm going to do. I'm going to write AD over BD times, next up, BE over CE, right? Times CF over AF. And I'm going to prove that equals 1, okay? How am I going to prove that? Well, isn't AD the same as BD? So where I see BD, I can just write AD instead, right? Right? That's true. AD over BD should be AD over AD. And BE over CE should be the same thing, right?
Wait.
And CF over CF is the same
You
thing.
don't have to write by substitution, right?
No.
I have a question.
But that's what we're doing. Good job.
I think I might have figured out another way to do it, but like I don't know what's against or what's not.
Okay, ask it.
Could you just like oh never mind.
Okay. So now we're here, right? We know this is true, right? Because all I did was substitute these guys, right? What is AD divided by AD?
1,
What's BE divided by E?
1,
What's 1 times 1 is 1?
2.
Done.
That was it.
That's it. That's medians. That's it. You pray that one's on there, right?
Mr. Matt. That was
That was easy.
All I did is I said, look, I have enough information right now to prove when I multiply those things together, it will be 1. So I did it, right? When you have enough information, show that it equals 1 and win. Oh, actually, one last thing. Sorry. By Siva's theorem converse, right? That says if this equals 1, then they're concurrent. Medians of triangle ABC are concurrent, and then you're done. Okay? So we got this, right? And so by Siva's theorem's converse, right, if all these multiply to 1, then they must be concurrent. We're done. All right, cool. Before we go on to prove angle bisectors, which is actually really easy too, I want to talk about angle bisector theorem. So that's page 8, I believe. The proof of angle bisector theorem. Nope, not page 8. Page 6. So, page 6 just tells you the theorem. It says that, look, if we have a triangle with an angle bisector in it, it cuts that triangle into 2 different triangles, right? It says that the sides of the angle we're bisecting, x and y, will be proportional to the bases. We cool with that? X over y will equal a over b, if that's an angle bisector, okay? Yes. Okay, bye. Let's prove this. This is kind of like a lemma to the proof that the angle bisectors are concurrent. So page 7. Here's what we're going to do. I'm never going to prove that these triangles are similar. There's not enough information. There are no shared angles. I've got nothing, right? I need AA or side angle side or something. I'm not going to get sides, right? I need angles. So what I'm going to do is I'm going to make another triangle. And the way I'm going to do that is by drawing a line that's parallel to this line, or this one, doesn't matter, right? I'm going to choose this guy. So I'm going to draw a line parallel to that and put it up here. I'm going to call that line CQ, okay, or whatever you want. And I'm going to say that it's parallel to this guy. Totally allowed to do that, right? I can make a parallel line whenever I want. Now that I've done that, I'm going to extend this guy out. Beautiful. And I'll call their intersection CX. So how do I write that? I say let CXQ exist and let ADX exist. And how do I know they intersect at X? Because they share that letter, right? Bye. Cool. Now that I've done that, I'm going to get these 2 triangles similar. Do you see any angles I can get together? There will be, but don't think that hard. Get the easy ones first. Yeah, right here. Right? So that's one pair of angles down. By vertical angles theorem, CDX, that angle is congruent to angle ADB. Cool. Where's my other set of angles? And yes, you should be looking for cap or alternate interior, right? Parallel, parallel, transversal, right? Oh, hold on. They gave us that AD bisects BAC, right? So these 2 angles are congruent, right? That was given to us. This is an angle bisector, right?
What's it called?
Yes. Alternate interior. This one and.
The one by the X.
Yep.
That's what I was trying to say.
Right?
I don't know what it's called.
This and this is what we have, right? Do you see it? So by alternate interior angles theorem, angle DAB, don't you dare, congruent to angle CXD. Now I have double angle, right? Which means they're similar. So by angle similarity, triangle ABD is similar to triangle. Let's match them up. X, right? B is the unknown, so it's going to go with C. And then D goes with D because it's vertical, right? So they're similar. All right, awesome.
So
Now,
ACD doesn't mean anything right now?
this triangle? No, we're not even going to use it.
Okay.
Actually, I mean, sort of, because guess what? Now that I have them similar, I can do CSP, right? So I'm going to get A and B together, right? And that's what I want. But I'm going to get Y with X is over here, little x, right? Sorry, I should use a different symbol, right? Algebraic X. So in theory, these both should be congruent, right? If I'm going to get them together. How do I prove that this, I'm sorry, not these are both congruent, that these are both congruent, right? If I'm going to get Y with X, Y goes with this, definitely, right? So this must be X if I can do it. How do I know that this is also X? What do you see?
I don't know. I see.
This is a really bad line. It should be straight across.
I was going to say that the A and the X are the same angle, so like that doesn't mean.
They are, yes. Big triangle.
Oh, isosceles.
It's an isosceles triangle. So by isosceles triangle theorem converse, these sides are the same, right? Do you see it? Two angles the same? So this must be the same as this, which means they're both X, right? So I'm going to say by isosceles triangle theorem converse, AC is congruent to angle or to XC, which implies that XC equals X, right? Sorry, I used X a bunch. We cool with that? So now when I do CSP, let me zoom out. I know that AB, this guy, right, which is Y, is going to go with XC, which is X. And that's going to equal BD over CD. BD, which is little b, over CD, which is little a. Flip and we're done.
How do you flip them?
Well, remember, if you do it to both sides, it's algebra.
Oh, okay, so you have to show.
What really happens is you multiply x over, multiply a over, and then divide by y, and then divide by b, right?
That's a lot of work.
Yeah, it is. So as long as you flip both, it's fine. It's algebra, right? So we're done. The hard part is knowing what to do, drawing the parallels, right? You'd never be able to guess that on your own, right? Somebody was really clever and came up with this, right? And then using alternate interior angles. That's the hard one to see, right? You could also do alternate interior here as well to get these guys. Instead of doing vertical, you could get these and these, right? That's fine. And then seeing the big isosceles triangle. But now you know. Okay, so we've proven that this is true. When you have a triangle with an angle bisector in it, x over y will be a over b, right? Okay, so now I'm going to prove that when I have angle bisectors in a triangle, they're concurrent. So let's draw some angle bisectors. I'm going to call that AD, and I'm going to have it bisect this. Okay? Whew, okay. So let AD exist and BDC, right? I need to show that they intersect. And then after that, I'm going to write that these angles are congruent. So angle CAD congruent to angle BAD. Cool? I'm going to do that for all the angle bisectors. So BE intersects with line AEC. Angle ABE congruent to angle CBE. All right. Do I know this proof off the top of my head? Yes, I do. Yes. Okay. I'm going to pause here. You might just keep going and doing that. I think the more I have on here, the harder it's going to be to see things. Do you see how AD breaks up this angle into two sides? Right? So by triangle angle bisector theorem, that's the thing we just proved, right? I know that the sides of this angle that I broke, right, will be proportional to the bases. So AC over AB will equal CD over BD. Again, you can use little letters if you want. I'm not writing little letters in, okay? It's way too much writing to prep that. We cool with that? Same thing here. It breaks it up into these sides, AB and BC. Okay. It'll be proportional to these two guys. AB, AE. And BC goes with this. C. Cool. I'm going to do it for this guy as well, right? And I'm going to prove they're all concurrent. So I got this. Let there be this guy. I'll do F. So let CF exist. And it intersects with AFB. And not only that, but it bisects the angles. So ACF is congruent to angle BCF. Rad? Okay. Then by triangle angle bisector theorem again, sides, bases. AC over AB equals AF over BF. Cool? All right, so now I'm going to show when I multiply AF over BF times BD over CD times CE over AE, they all equal 1. Okay? It's time. We have enough information. So AF over BF times BD over CD times CE over AE. And what does that equal? Well, if you look, AF over BF, it equals AC over AB, doesn't it? Right? So I'm going to write that. BD over CD, that's this guy. It's just flipped, right? So it's AB over AC. Are you seeing what I'm seeing?
Does it matter if you flip it or not?
As long as you flip both,
Okay.
right? See how I did BD over CD, so I wrote AB over AC? Right? The order matters because now look, right? You see what's happening here? And then lastly, CE over AE. CE over AE is AB over BC. So CE, AE, BC, AE, AB. Wait, what the? Did I write one of these twice? I feel like I wrote one of these twice.
AB and AC.
I screwed this up. AB and AC go with BD and DC. So AB and AC go with BD and DC. That's fine. AB and BC go with AE and CE. Good. AC and BC go with AF and BF. Where did I goof this up? CE, AE. BD, CD, AB, AC, AF, BF, AC, AB. What did I goof? Did I use letters twice? These two cancel. These two cancel. These don't. They should. What did I screw up? CAD, CBA.
I wrote AB 3 times. Why?
What do you mean?
I don't know. AB's on there.
AF, BF. BD over CD, CE over AE. AF over BF is ACAB. BD, CD, AB, AC. CE, AE is BC, AB. I'm losing my mind. AC, AB. Did it. Oh, I wrote ACAB twice. Is that what you're trying to tell me?
Yeah.
Okay, good. Yeah, we don't want that. I did AC and AB. I did AB and BC. I need to do this one. AC and BC. That was my bad. So AC goes with AF. And, right? AC goes with AF. And BC goes with BF. There we go. AFBF. This is AC over BC. There we go. 1. By Siva's theorem, converse, angle bisectors of triangle ABC are concurrent. Good?
Yeah.
All right. So the key was we needed to use that angle bisector theorem to get this thing, right, the congruency. And then when we have it, we switch and go. That's it. That's the pattern. That's the pattern, right? Median's way easier, right? They're the same. They're the same. They're the same, right? We win. This is these guys go together to, right? It's a little bit more complicated, right? But it's the same premise. We good? All right. That's page 8. Page 9. If it fell down, don't put it back up because it'll fall down during tomorrow's review and then everybody will lose their crap, right?
I put a tape on it.
Okay.
Like on the bottom.
If it fell off, though, we're going to leave it off because I don't want it falling off again, right? And people will lose their mind and their focus. All right. Let's look at 10. And then we're basically done. We just have to do Siva's theorem's converse, okay? So, perpendicular bisector theorem. It says, if you've got this, you need to go.
No, I'm good.
Okay, if you've got this, then it implies this, meaning that any point on the perpendicular bisector, like this point here, will always be the same distance to the endpoints of the other segment. Always. Any point. And as you go down that flagpole, right, eventually you get to here, and is that equidistant from these 2 points? Yeah, it is, right? So it's just saying like the midpoint, if you extend it up, it's still going to be like kind of a midpoint between them, right? So we're going to prove that. D is on the perpendicular bisector of ABC. Yes, it is. That's a perpendicular bisector, right? We're going to prove that D is equidistant from them, right? So here's what we're going to do. First, let AD and CD exist, right? Let's bring those into the picture. And now we're going to prove those are congruent. Well, we have 2 triangles. How do we prove parts congruent? First, we what? If we want to prove the parts of a triangle is congruent, what do we do to the triangles first? We prove that they are congruent, right? So how am I going to prove these 2 triangles congruent? We've got a side and an angle. We're not going to get HL, right? Because if we had H's matching, we'd be done. What do you see? Marissa, we get this?
Shared side.
Yep. Right. And now how do I know they're congruent? Nice. And if the triangles are congruent, what do I do to get their parts congruent? Because they're congruent, right? By CCP, AD, CD, and we win. So by definition, D is equidistant from A and C, right? I write that and I'm done. Yes?
I never really learned like the CCP thing because I was gone for like the whole lesson.
I got you. If triangles are congruent, corresponding parts will be congruent. Corresponding means same relative spot, right? Mm-hmm. See how AD and CD are in the same relative spot, 1 and 3? So they must be congruent. So after you get triangles congruent and you write your letters carefully, then you know that these must go together. So you win.
Okay.
Now, did you want to prove angles congruent? Well, then DAB and DCB would be congruent. DAB and DCB would, right? And if you match up the order of the letters, all those things will be congruent. So if you wanted to prove that DB is congruent to DB, look, DB, DB. Anything you want. Angles in 3s, right? Letters, 3 letters. Or segments in 2 letters. Yeah. I am not a crook. All right, converse of this. It's the reverse. Page 11. That's fine. That makes total sense. You're crazy for being here. I hope your parents don't think I'm keeping you here on purpose. Like, it is not me. Okay. I happen to be here. You asked me to stay late. Okay.
My mom makes me, and like I know I need to, obviously.
Yeah, that's a good thing.
She's like, you should have gotten me yesterday, and it's your priority.
All right, the converse says that if a point is equidistant from the endpoints of a segment, right, then that point must be on the perpendicular bisector of that segment. It's true, right? Must be. So we're going to prove that if D's here, equidistant from A and C, it's on the perpendicular bisector of AC. Okay? So first off, we're going to say, let there be. Now, we are allowed to drop a 90 whenever we want, right? We're also allowed to let there be a midpoint. So it's your choice. Do you want to make this a midpoint first and prove that that's 90? Or do you want it to be 90 and prove that that's a midpoint?
Let's do 90.
Yeah, so let's drop a 90. Right? Do I know that it's in the middle? No, I can't make all that happen. I can't go vertex 90 and midpoint. Too much, right? We talked about that, right? 2 of the 3 is fine, not all 3. So let DB exist and have it be perpendicular to ABC. Now, we didn't make it a perpendicular bisector. We made it perpendicular,
Okay.
right? We're going to prove it's a perpendicular bisector, okay? That's the bisection part. You can assume the bisection, right, the midpoint, or you can assume the 90. I'm assuming the 90, okay? So I'm going to assume this. Now, how do I prove that these two are congruent? Because if they're congruent, then that is a perpendicular bisector, right? Well, I proved the triangle's congruent. How am I going to do that?
House.
Shared side. We do get asked, don't we? But what do we know about this? Shared side, right? We get asked, but what?
It's 90.
So hypotenuse and leg, right?
Yeah.
So we're good. By HL, triangle ABD, congruent to triangle CBD. Nice. And if they're congruent by CCP, these guys are, right? And if you look, AB and BC, same spot, right? Therefore, by definition, this is a perpendicular bisector and D is on it. How do I know D is on the perpendicular bisector BD? How do I know D is on BD? It's in the name, right? How do you know B is on ABC? Because it's in the name, right? So by definition, BD is a perpendicular bisector and D is on it. I'm not going to write anymore. We cool with that? All right. Using that as our lemma, we're going to prove that perpendicular bisectors of a triangle are concurrent. Okay? I'm going to make some perpendicular bisectors, okay? So I'm going to say, let this be the midpoint over here. I could have done this side, but I'm doing these two because it's easier to see the last bit if it's at the bottom, okay? And I'm going to say that's 90, okay? I'm going to call this point D, and I'm going to call this E. Notice I didn't connect it to A. We can't assume all that at once. We can assume midpoint, we can assume 90, we can't assume vertex at the same time. So we'll wait on that. I'll do this one as well. And I'll call that F and G. And they do intersect at some point, right? I'm going to call that K. That's totally valid. 2 lines intersecting happens all the time. We can't assume the third one would go through it, though. Right? If I drew the third one, that it would go through it. I'm going to prove that it has to, though. Okay? So I'm going to say let F, K, G exist, and let it be the perpendicular bisector, right? See the difference in the symbol? Of AFC. And I'm going to say let DKE exist. And let it be the perpendicular bisector of CDB. Okay? Right. And how do I know they intersect at K? Because they both have K, right? We cool? Now I'm going to prove that the next one has to go through it. And here's how. Isn't K on a perpendicular bisector? That means it's equidistant to the endpoints of that guy's segment, right? We proved that earlier, right? That's perpendicular bisector theorem. So because K's on this perpendicular bisector, right, it's equidistant to its endpoints. We cool with that? CK congruent to BK, right? Isn't K also on this perpendicular bisector? So it's going to be equidistant to AC, A and C, right? It's already equidistant to C. I'm going to show that it's equidistant to A. Now here's my logic. No perpendicular bisector on this side yet, right? So, by perpendicular bisector converse, K is the same distance from A and B, isn't it? If we have a point that's the same distance from 2 others, right? Don't we know it has to be on the angle bisector, or perpendicular bisector, right? Right? So it's the same distance from A and B. Therefore, it must be on AB's perpendicular bisector. It must be. So by perpendicular bisector theorem converse, K is on the perpendicular bisector of AB. Right? Cool. Well, if it's on AB, it's perpendicular bisector. And it's on BC's perpendicular bisector. And it's on AC's perpendicular bisector. Those are all three sides of the triangle, right? They all go through K. Well, if they all go through K, they're concurrent, right? They all go through K. So they're concurrent to K. So therefore, this. Done.
That's the hardest one.
Yeah.
Mm-hmm. It is. It is.
It was also the whole, like, based off the whole problem I got wrong on last week's test. Like, the
Oh, kind of, yeah. Yeah. What center do the perpendicular bisectors make?
a circumcenter.
Yeah. These are all radii. Right?
Yeah, I got
There's a
that.
circle, right? So, of course, it's equidistant from all those. Now, we don't know that the circumcenter exists. We're proving it exists, right? That they all do intersect at one point. But that's why it has that special property, right? It's the center of a circle that goes around the triangle. That's kind of rad. Now, the hardest one is where you have to do the small triangle, right?
That one's crazy.
It is, but it's not hard. It's just a lot of drawing and alphabet soup. We're going to hit it first thing again tomorrow in class, and I'm going to go through it quick because I got it. We got other things to do, right? Tell your friends they need to study and need to watch this video because there's no way in hell we're going to get through all this in 45 minutes, right?
Especially.
With everybody asking questions?
Yes.
Yes, no way, because tomorrow is when everyone's going to be like, I actually want to learn this material, Mr. Mack. Please answer all of my questions. And I will, but where we end up is where we end up, right?
Yep.
Okay. This was live. All right, goodbye. I love you all.